Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we looked, that is we concluded our discussion on SCFDMA, that is single carrier frequency division multiple access, which is one of the solutions to reduce PAPR in an OFDM system. And we said in SCFDMA, we introduced two blocks, one is the equalization and demapping block, the other is the M point IFFT to essentially reverse the M point FFT that is done at the transmitter in this SCFDMA system. In addition, we said that this subcarrier mapping from M to M, that is at the output of the M point FFT to the input of the N point IFFT, is a critical aspect of an SCFDMA system, and we said there are many ways to do it. One is to interleave zeros in between, that is you space your M outputs of the FFT regularly over N and interleave the elements in between with 0, and this is known as interleaved FDMA or IFDMA. And we said the other is to simply use a zero padding, that is stack everything in the beginning and fill the rest of the elements with zeros. This is known as LFDMA, and this is employed in the uplink of LTE, which is of course the 4th generation wireless mobile standard. All right, and with this we concluded our discussion on OFDM. We summarized the various aspects that we looked at in OFDM, and then we moved on to wireless channel modeling, in which we said the wireless channel decreases as the signal strength decreases in a typical wireless scenario as a function of the distance. And in order to characterize cellular scenarios, that is the power that is received as at the cell edge and so on, or to characterize the transmit power, we wanted to understand these channel models. And we said typically in free space the channel power decreases with the square of the distance, that is the path loss exponent is 2, that is power decreases as d square. All right. However, we wanted to look at other urban scenarios, in which cellular scenarios typically in which there are obstructions, and we said the path loss exponent in such scenarios can be higher. We started looking at a ground reflection scenario, in which between the base station and the mobile there is a line of sight path, and there is also a ground reflected path. The line of sight path has a distance d LOS, the ground reflected path has a distance dg, height of the transmitter is ht, height of the receiver is hr, the distance between the horizontal distance between transmitter and receiver is d, and we wanted to look at the received signal strength as a function of this distance d, and we said the total received signal strength E total is E LOS plus Eg, that is the point at which we are. So, let us continue from this point in the lecture today. And we said that E total received signal total received field strength E total is simply the LOS plus the ground reflected. This is the ground reflected path. This is simply the sum of these two components. This, let me mention, this is reflected from the ground. And let us consider, similar to what we had done earlier, let us consider a reference strength of E naught at distance d naught, that is I am considering this as my reference, that is E naught is the signal strength at the distance d naught. Then my E LOS, the LOS received signal strength E LOS is given as follows. E LOS is nothing but E naught d naught by d LOS, because remember the power decreases as d square, the signal strength simply decreases as, or the amplitude decreases as 1 over d, and the phase factor of course, which is the most important thing, that is given as 2 pi f c and a function of the delay arising because of function of the propagation delay arising because of the distance. This is simply the propagation delay which results the phase difference at the receiver, that is the phase difference between the receiver and that is the phase lag at the receiver compared to the transmitter. And this I will approximately, what I will do is approximate d LOS by d for this component, for the signal strength component, and I am going to simply write this as E naught d naught by d e to the power of j 2 pi f c t minus d LOS by c. Okay. All right. Now, similarly, of course, we have another component which is the ground reflected component, and this ground reflected component, I am going to write this ground reflected component as follows. Similar to above, the strength is E naught d naught, again I am going to approximate dg by d into e power j 2 pi f c t minus dg. This is the propagation delay which is related to the distance dg. However, there is also now a factor of -1, and that arises because of the ground, that is the phase inversion at the ground reflection. So, this essentially arises because of the phase inversion from ground. This arises because of the phase inversion from the ground reflection. Now, the received signal is nothing but the sum of these two signals, that is E LOS and E R, and hence the total, as we had said before, is nothing but E LOS plus E R, which is essentially E naught d naught by d e to the power of minus j 2 pi f c t minus d LOS by c minus E naught d naught by d e to the power of minus j 2 pi f c t minus dg by c, that is, remember this first term is E t naught, second term is E r, and the minus arises because of the phase inversion at the ground reflection, and this is nothing but E naught d naught by d into e power minus j 2 pi f c t minus d LOS by c over c into times 1 minus e power j 2 pi f c delta d over c. All right. We are isolating this term E naught d naught by d into this phase term times 1 minus e power j 2 pi f c delta d over c, where this delta d is an important factor. This delta d is essentially the difference, that is this difference, the path length difference, that is difference between the distance of the length of propagation in for the ground reflection minus the length of propagation for the line of sight path. And this I am going to simply write as follows. This is E naught d naught by d e power minus j 2 pi f c t minus d LOS by c into 1 minus e power j 2 pi and delta d over c over f c is nothing but lambda, hence I can write this as delta d over lambda. Okay. So, I am going to write it this way. Essentially this is essentially what we said, this is the E total, which is E line of sight plus the E reflected, and there is a minus sign because of the phase inversion at the ground reflection. Here for this simplification we have used the fact that c over f c, that is velocity over carrier frequency, is nothing but lambda, which is essentially the wavelength of the wave. Okay. And this I can further simplify as follows. This is E naught d naught by d e power minus j 2 pi f c t minus d LOS by c into e power j 2 pi delta d divided by 2 lambda times e power minus j 2 pi delta d divided by 2 lambda minus e power j 2 pi delta d divided by 2 lambda, and this factor, of course, this is nothing but sine of 2 pi delta d divided by 2 lambda. Hence, net I can write E total equals I am sorry, this is of course minus sign, hence I can write this as E total equals minus E naught d naught by d e to the power of j 2 pi f c t minus d LOS by c into e power j 2 pi delta d divided by 2 lambda into sine 2 pi delta d divided by 2 lambda. Look at this difference between the distance, that is difference between the distance d g minus d LOS, that plays a critical role. This is nothing but the difference in the propagation distance, and naturally because the phase lag that is there in these two ways depends on the distance, hence the phases with which they add depends on that difference of the distance, which essentially determines what is the resultant amplitude. And finally, if I look at the magnitude of E total, both these exponential factors, they vanish because they are phase factors, hence the magnitude is nothing but E naught d naught by d magnitude sine 2 pi delta d over 2 lambda, all right. And this is essentially the expression that we have for the net magnitude, where delta d, let me remind you again, is nothing but dg minus dLOS. This dg is the path length or the distance of propagation of the ground reflected component, propagation distance of ground reflection, and this dLOS is the propagation distance of LOS of the line of sight component. Okay. So, now what we have to do is we want to simplify this expression further, which means I want to simplify this delta d, which is the difference between distances dg and DLOS. So, first I will start by computing both DG and DLOS. So, let me start first by computing the easier one, that is DLOS, and for that let me go back to the diagram. We have height of transmitter is HT, we have height of receiver is HR. Hence, if I draw this line of sight component DLOS, let us look at this triangle. This distance is the horizontal distance, which is D, and also I have the height of this triangle, which is now HT minus HR. This is a right angle triangle with sides HT minus HR and D. Hence, DLOS is nothing but square root of HT minus HR square plus D square. Hence, DLOS is HT minus HR square plus D square. Similarly, now let us compute DG, that is slightly involved, but nevertheless again intuitive. I have this over here, I have again HT, HR, I have the ground reflected component such that theta incident is basically theta reflected at the length of the ground reflected component. DG is nothing but the sum of these two components. What I will do is I will use the method of images. I am going to extend this below by HR, and I am also going to extend this below. You can see that these two are equal in length. Hence, this now is nothing but DG, and hence if I look at this triangle, essentially with distance length D, and this length now becomes obvious, that is HT plus HR. Hence, this is DG is nothing but the side of a right angle triangle with sides HT plus HR and D. Hence, DG is square HT plus HR whole square plus D square. Hence, what I have net is essentially delta D equals DG minus DLOS, which is basically HT plus HR whole square plus D square minus HT minus HR whole square plus D square, which if I take D common outside, this is square root 1 plus HT plus HR by D whole square minus square root 1 plus HT minus HR by D whole square. All right. And here I am going to use an approximation that HT comma HR are much smaller than D. So, HT plus HR, HT minus HR, so on and so forth, all are much smaller compared to D. Hence, delta D is approximately D into 1 plus half HT plus HR by D whole square minus 1 plus half HT minus HR by D whole square, which is essentially equal to D times, if I simplify this, the ones cancel, this is a half HT plus HR whole square minus HT minus HR whole square, which is essentially 4 HT HR by D square, which essentially is equal to 2 h t h r by d. Hence, what we are saying is this delta d distance, this is approximately equal to 2 h t h r by d. Hence, delta d approximately equal to 2 h t h r by d. Let me again remind you what these quantities are. H r is receive antenna height, h t is the transmit antenna height, and d is the horizontal distance between transmitter and the receiver. Okay. So, this is what we have. We said delta d, which is the difference between the paths dg minus dlos, this is equal to 2 h t h r by d, where h t is the transmit antenna height, h r is the receive antenna height, and d is the horizontal distance between the transmitter and the receiver. Now, I am going to substitute this delta d back in the expression where we are saying magnitude E total is nothing but twice E naught d naught by d into sine 2 pi delta d by 2 lambda. I am going to say, since delta d is fairly small, I am going to say this is approximately equal to 2 E naught d naught by d 2 pi delta d divided by 2 lambda, since for small theta sin theta is approximately equal to sin theta. And now, I have this essentially I am going to replace by 2 lambda into 2 h t h r by d, which is essentially equal to 4 pi E naught d naught h t h r by lambda d square. Hence, magnitude or received signal strength, the most important idea here is that the magnitude of the received signal strength is proportional to 1 by t square, which implies the power that is received. Since the magnitude of the strength, signal strength is proportional to 1 over d square, the power naturally is proportional to 1 over d to the power of 4, since the power is proportional to the square of the signal strength, which means the path loss exponent, the powers now decays as the fourth power of distance. Hence, this means path loss exponent equals 4. Hence, when we have abstractions now, essentially when you have reflections and so on, the path loss exponent essentially increases, all right, and which is typically what we expect in urban and cellular scenarios. Hence, again going back to our free space loss equation, one can write the received power in dB is P tilde some reference power at distance d naught minus 40 log 10 d over d naught, which says that there is a 40 dB per decade kind of decrease in the power. P tilde is some reference power at distance d naught. This essentially is the main aspect, is the major aspect which says, which arises because path loss exponent n equal 4, and this is essentially 10 times n. Okay. So, that is what we are saying. Essentially what we are saying is that in urban scenarios or in cellular scenarios, because of the reflection and scattering, what we might have, we do not have free space propagation, which means in essence what we are going to have a lot of interference, and we are going to have reflections, scatter components adding up. Hence, the effective path loss exponent, if you look at it at the receiver, it looks larger than 2, it is in the range of 2 to 4. And let us look at some tabulated scenarios in practice. Let us go to this table. If we go to this table, we can see path loss exponent for various scenarios. For free space it is 2, for urban cellular radio it can be anywhere from 2.7 to 3. So, it is around 3. In shadowing, in fact, it increases from 3 to 5. So, it can reach as high as 5. In building, in line of sight, as you can see, it is lower than this thing, and especially if you have obstructions, it rises even beyond 4 and 6. But normally in outdoor cellular scenarios, this path loss exponent essentially this is of the order, of 2 to 3. All right, n equals 2 to 3. I mean, this is of the order of 2 to 4, on an average around 3, 3.5 and so on. All right, it depends on the exact scenario that you are considering. Okay, so that is essentially our discussion on the path loss scenario. Now, precisely to calculate or give us an approximate idea of what is the received signal strength in several urban scenarios, there have been several models, standard channel models that have been proposed, taking into a lot of these urban suburban sort of factors into consideration, that is to give us an idea of how to accurately or more or less accurately predict the signal strength at a certain distance. These are, for instance, Okumura model, that is one such model, and the next we are going to look at this model. So, to characterize the distance signal strength in urban scenarios, we have several models. The Okumura model is one such model. Simply put, it states that, so first let me again reiterate point, several models have been developed to accurately model the received signal strength in practical wireless scenarios. The keyword here is practical. In practical Alright, so the several models that have been developed essentially to characterize this wireless signal strength in practical scenarios, especially cellular scenarios and so on. And the Okumura model is one of the most widely used such models essentially for signal strength prediction in urban suburban areas. So, this Okumura model is one of the more popular models. So, let me summarize that point here. The Okumura model is one of the most widely used analytical models for signal strength prediction in urban / suburban areas. This is one of the more widely used models, and even though this model, the Okumura model, is valid from 150 to 1920 megahertz, this can be extrapolated for higher frequencies. So, it is valid from 150 to 1920 megahertz. This is the range of the carrier frequency. However, with extrapolation it can be used for higher frequencies. It can be extrapolated however, it can be extrapolated for higher frequencies. So, what you are saying essentially is this Okumura model is one of the more popular models employed to characterize signal strength in urban practical scenarios such as urban, suburban, cellular scenarios, and it is one of the most widely used analytical models, and it's can be used right around the 200 megahertz range to essentially we are going to use it for the 2.5 gigahertz range also, essentially about covering most of the cellular band essentially. Okay. So, what is the Okumura model? If you will look at the model, Okumura model, it predicts the 50th percentile loss, the 50th percentile loss or the median loss or median path loss is given as. What is the 50th percentile? 50th percentile is essentially saying that half of the measured values lie above this, half of the measured values lie below this. So, that is the essentially the same as the median path loss. Alright. So, the 50th percentile or essentially the median path loss is given as L50 in dB, which is the 50th percentile path loss, is LF, which is the free space path loss, plus we are going to see what each of these factors is shortly, A mu, which depends on the frequency, that is the carrier frequency and the distance, minus the gain, a gain factor arising out of the transmit antenna, minus a gain factor that is arising out of the receive antenna, minus a gain factor that is arising out of the area. This is a path loss. So, all the gains have to be essentially subtracted from the loss. L50 dB, let us explain what each of these components is. L50 dB, as we already said, is the 50th percentile path loss in dB, which essentially says it is the median path loss. This essentially means this is the median path loss, and 50% of the measured values lie above this threshold and 50% of the measured values lie below this threshold. So, 50% of measured values lie above this threshold and 50% lie below 50% lie below this threshold. LF, the factor, the other factor is essentially the free space propagation loss. This is the free space propagation loss. We are going to characterize this slightly. This LF is the free space propagation loss. GHTE is the transmit antenna height gain factor. This is not to be confused with the gain of the transmit antenna, but this is a gain arising out of the height. Hence, this is the transmit antenna height gain factor. It is dependent on the height of the transmit antenna. Similarly, GHRE is the receive antenna height gain factor. That this gain is arising because of the gain of the height of the receive antenna. And normally you can see, if the transmit antenna and receive antenna are mounted high, then there is less obstruction, which means less interference, which means more energy that is received at the receiver. So, as a function, as the height increases, these gains increase, which means these subtract from the path loss, therefore, the effective net path loss decreases. Essentially, that is what this means. And G area is the gain due to environment, equals this is the gain due to the environment. For instance, let us go to the free space path loss. LF equals the free space path loss. We already said in free space the received signal power as a function of distance is nothing but Pt equals Gt Gr lambda square divided by 4 pi square d square L, where Pt is the transmit power, Gt is the transmit antenna gain, Gr is the receive antenna gain. Remember, these are the radio frequency gains. Lambda square is the wavelength, 4 pi square, and d square is the distance, and L is the system loss factor. Let us assume a normal scenario and let us set Gt equals Gr equals L equals 1, that is, I am considering normal antennas where the gain factors are 1 and there is no system loss factor, in which case this becomes equal to Pt lambda square by 4 pi square d square, which essentially can be written as Pt divided by d square divided by 4 pi whole square lambda square, and this is now nothing but this factor d square divided by 4 pi square lambda square is nothing but, this is nothing but the free space path loss. This is nothing but the free space path loss. Hence, the free space loss is equal to 4 pi square d square divided by lambda square. Hence, the free space loss in dB is nothing but 10 log 10 of 4 pi whole square d square by lambda square. This is essentially the free space loss in dB. So, this is the expression for the LF component. Now, let us look at the Tx and Rx antenna height gain factors. Let us now look at the transmit and receive antenna height gain factors. And again, I would like to stress that these are not the gains of the transmit and receive antennas, but these are the reductions in the path loss or the gains that are arising because of the mounting height, that these are the height gain factors which result in less obstruction as the height increases, hence reduction in the path loss. All right. So, please make that distinction. So, GHTE, which is the transmit antenna height gain factor, is given as 20 log 10 HTE by 200. Okay. That is, this is the transmit antenna height gain factor, and the receive antenna height gain factor GHRE, that is given as follows. That is given as 10 log 10 HRE by 3 if HRE is less than 3 meters, and that is given as 20 log 10 HRE divided by 3 if 3 meters less than HRE less than 10 meters. All right. So, we are saying there are two gain factors. The first one, this is the transmit antenna height gain factor, and the second is essentially the RX antenna, the receive antenna height gain factor, and GHTE as a function of the transmit antenna height is given as 20 log 10 HTE or 200, and GHRE as a function of the receive antenna height is given as either 10 log 10 HRE by 3 if HRE is less than 3 meters, or 20 log 10 HRE divided by 3 if HRE is in the range of 3 meters and 10 meters. And the other components, which are A mu Fc comma d, which depend on the carrier frequency, this is essentially a correction factor, is essentially a correction factor. This is essentially a correction factor as a function of carrier frequency Fc and distance d. As a function of the carrier frequency Fc and distance d, and these have been tabulated. Actually, these have been tabulated for several values, several frequencies and distances. These, or rather, have been plotted. These have been plotted for several values of carrier frequency Fc, several values of Fc and d. For instance, let me go to that plot and show you how that plot looks like. For instance, if you look at this, I have the Okumura model. I am the A mu factor as a function of frequency and distance. For instance, you can see on the this axis there is one curve for each distance, 1 to 1 kilometer, 2 kilometer, 5 kilometer, up to 100 kilometers. For instance, if I want to look at what is the A mu factor at 1.8 gigahertz, that is, I want to look at 1.8 gigahertz or 1800 megahertz, essentially corresponding to a distance d equals 5 kilometer. I have at 1.8 gigahertz, I look at essentially basically what it is, and this is the curve. Remember this curve here, this is the curve for the distance of 5 kilometers, and you can see that that factor is something around 28 dB. So, that A mu f d at 1.8 gigahertz and 5 kilometers is roughly about 28 dB. Hence, if I go back here, for example, the Okumura model, A mu at d equals 5 kilometers and f c equals 1.8 gigahertz is 28 dB. That is, if you write A mu of 1.8 gigahertz at distance 5 kilometers, that is nothing but 28 dB. all right. So, if you look at that factor essentially is this mu factor in this example is 28 dB, and similarly let us come to the other factor. The other factor is this G area factor, which is an area or environment dependent factor. The other factor in the expression is G area, which is essentially it is a correction factor for various environments. It is a correction factor for various environments, and it has been computed for different frequencies. Has been computed and plotted essentially for different frequencies. This has been computed and plotted for different frequencies for a particular set of areas, for areas of the type suburban, quasi open and open. So, this has been computed and plotted for suburban, quasi open and open area. So, this is G area is again an area correction factor which essentially exists in the model, because let us say you go from because the Okumura model is actually meant for an urban scenario, but if you move from an urban to suburban scenario, obviously the clutter decreases, hence the loss also decreases, and then if you move to an open area, then you would expect only the free space loss, because there is no obstructions as such. Hence there is a correction factor essentially as you move from urban area to suburban areas to open areas. For instance, if you look at that plot, that looks as follows. For instance, if we look at this G area plot, for instance, again I go back to the same question, that is 1.8 gigahertz, and of course, this is does not depend on the distance. If I want to look at 1.8 gigahertz for a suburban area, I go to this point, which is 1.8 gigahertz, which is essentially around this, and this again is the plot for the suburban area, and you can see this is approximately this is approximately 12 dB. So, in essence I go back to this thing. So, what we can say is, for example, for a suburban area at 1.8 gigahertz, the G area factor is 12 dB, that is there is a gain of 12 dB, which means 12 dB subtracts from the path loss essentially for this suburban factor at 1.8 gigahertz. All right. So, that is what this means. So, that G area factor is essentially 12 dB for this suburban area. So, that comprehensively characterizes the Okumura model. So, let us look at a simple example essentially to solidify our understanding, essentially to illustrate the practical utility of this Okumura model. So, I want to look at an example here of how to use the Okumura model in practice. So, what the example we are going to consider is as follows: employing the Okumura model, compute the median loss, which is nothing but the L50, compute the median loss at a distance of 8 kilometers when the carrier frequency F c equals 2.1 gigahertz, H T E the transmitter height equals 40 meters, H R E equals 2 meters in a large city. All right. So, what we want to do is we want to employ the Okumura model to find out in an urban propagation environment, that is in a city at a distance of 8 kilometers, which are typically the radius of cellular environments, cellular base stations, that is 5 to 10 kilometers, and a carrier frequency of 2.1 gigahertz, transmitter mounted at height 40 meters and a receiver height 2 meters, roughly slightly larger than the height of a normal person, which is around the 1.5 to 2 meter range, that is the extreme range of height of a person, that is 2 meters. What is the average, what is the average path loss look like, which will give us an idea of what is the transmit power that has to be transmitted by the base station. So, that is to account for this path loss essentially. So, let us start by computing that. We are given F c equals 2.1 gigahertz, which is again 2.1 into 10 to the power of 9 hertz, and we also know that this lambda value, lambda equals 3 into 10 power 8 divided by 2 into 10 power 9 equals 0.143 meters. This is nothing but the velocity of light. This is c, this is F c, and c by F c equals lambda, which is 0.143 meter. Hence, the free space path loss we know is 4 pi d square divided by lambda square. Hence, free space path loss L f equals free space or free space loss equals 4 pi square d square divided by lambda square, which is 4 pi square into 8 kilometers, that is 8 into 10 power 3 whole square divided by lambda square, which is 0.143 square, and this is equal to, and in dB this is nothing but L f in dB is 10 log 10 of 4 pi square into 8 into 10 power 3 square divided by 0.143 square equals 116.93 dB, which is essentially 117 dB. All right. So, that is what we are saying is the free space path loss if there is no obstructions. This is what the path loss would be, but obviously in a city environment we would have a lot of obstructions leading to scattering and reflection. So, what would the additional factors be? First, we have to look at the transmit antenna height gain factor, that is that H T E. We are given that the transmit antenna height H T E equals 40 meters, implies G of H T E is 20 log 40 divided by 200 equals minus 14 dB, and of course, we are going to have again another factor that is arising because of the receive antenna height. So, again due to lack of time here I am going to end this lecture here, and I am going to start covering again complete the rest of the example and move on to a different topic in the next lecture. Thank you very much.